Hello, welcome back, wherever you are tonight. And I wonder, genuinely, at this hour, what particular corner of stillness you've found, what quality of light or dark surrounds you, what small, familiar sound nearby tells you exactly where you are without needing to open your eyes. I'm glad you're here. This is a good hour to have arrived at. Whatever the day asked of you, it's behind you now. Go ahead and settle in properly. Not the tentative kind, still half listening for one more thing to happen. The complete kind. Let your weight sink entirely into whatever is holding you up. Let your shoulders finally set down whatever they've been carrying. Let your breathing slow into its own rhythm, unmanaged, unforced. You don't need to hold on to anything tonight. What stays with you will stay because it found something in you already waiting for it. The rest will simply pass through, gently. And that's exactly as it should be. This isn't a lesson. It's a long, slow unfolding of something true, offered at whatever pace lets your eyes close on their own. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down until they fit the shape of a quiet evening. If this feels like somewhere you'd like to return to, a gentle like or subscribe helps other people find their way here too, on their own restless nights. But that's for later, for the more awake hours. Right now, there's only this. Tonight, we're going to spend our time with an old friend. One we've visited before, in other conversations, but one that deserves, I think, a proper, patient, unhurried evening entirely its own. Because right now, this year, this particular season, something genuinely remarkable is happening to it. Something that has never happened to any object built by human hands in the entire history of our species. Voyager 1. Right now, tonight, as you lie wherever you're lying, this small, aging spacecraft, built in the early 1970s, launched in September 1977, roughly the size of a small car, is approximately 15,800,000,000 miles from Earth. 25.5 billion kilometers. A number so large that, in a few minutes, we're going to need to build it slowly and carefully, the way we build all our large numbers here at Late Space, because simply saying it aloud doesn't let it properly land. And in November of this year, 2026, Voyager 1 will cross a threshold that no human-made object has ever crossed before. It will become, for the first time in history, one full light day away from Earth. A distance so vast that a radio signal, travelling at the fastest speed anything in the universe can travel, will require a full 24 hours simply to make the one-way journey between this small, faithful machine and the antennas here on Earth still listening for its voice. Tonight, we're going to talk about what Voyager 1 has found across nearly 50 years of continuous, patient travel. Not just the famous discoveries from its early years, sweeping past Jupiter and Saturn in a blaze of scientific triumph, but also the quieter, stranger, more recent findings. The things it has been telling us, faintly, patiently, from the genuine dark between the stars in the years since it left our solar system behind entirely. Close your eyes when you want to. Let's begin. Let's start, properly, with scale. Because I think understanding exactly how far 15,800,000,000 miles actually is the necessary foundation for everything else we're going to discuss tonight. If you were to drive a car at a steady highway speed of 70 miles an hour, continuously, without ever stopping, it would take you more than 25,000 years to cover this same distance. Light itself, the fastest thing in the entire universe, the thing that reaches your eyes from the sun in about 8 minutes and reaches you from the moon in about 1.25 seconds, requires nearly 23.5 hours, right now, tonight, simply to travel from Voyager 1 back to Earth. Let that specific detail settle for a moment, because I think it's genuinely worth sitting with. If, right now, at this exact moment, an engineer at NASA's Jet Propulsion Laboratory sent a command to Voyager 1, asking it, say, to check the status of one of its remaining instruments, that command would not arrive at the spacecraft until tomorrow morning, our time. And whatever response Voyager 1 sent back, immediately upon receiving that command, wouldn't reach Earth until the day after that. A conversation with Voyager 1, in other words, unfolds not in seconds, not in the comfortable back and forth we're accustomed to in ordinary daily life, but across the span of nearly 2 full days for a single question and a single answer. And this delay is growing. Every single day, Voyager 1 moves an additional 1.4 million kilometers further away, traveling at a steady 17 kilometers per second, a velocity it has held remarkably consistently since a gravitational assist from Saturn back in November of 1980, more than 45 years ago, by the specific date of November 15th, 2026. A date NASA's own engineers have calculated with careful precision. Voyager 1 will have reached a distance of 25.9 billion kilometers from Earth, and the one-way signal delay will reach exactly 24 hours, 1 full light day, a threshold no human-made object has ever crossed before, and, quite possibly, none will cross again for a very long time. Wherever you are, I hope you're comfortable. Let's take a moment here before we go any further, because I want this specific milestone. 1 light day to properly settle the way we let all our large ideas settle here at Late Space before we move forward into the story of how Voyager 1 actually got this far and what it found along the way. Voyager 1 was never originally intended for this. When it launched from Cape Canaveral on September 5th, 1977, just over 2 weeks after its twin, Voyager 2, had already departed on a slightly different trajectory. Its planners at NASA had designed it for a mission expected to last approximately 5 years. 5 years to fly past Jupiter and Saturn, gather what data and images it could, and then, quietly, faithfully, continue outward into the dark, its primary scientific work considered complete. Nearly 50 years later, it is still going. Still, remarkably, faithfully sending back data. Still, even now, teaching us things about the universe that no other instrument, not Hubble, not Webb, not any of the sophisticated ground-based observatories built in the decades since Voyager's own launch, is capable of directly, physically measuring, simply because no other instrument has ever actually been to the specific place Voyager currently occupies. This is, I think, worth properly appreciating before we move any further. Voyager 1 is not simply old. It is ancient by the standards of human technology, built using computer systems with less processing power than a single modern digital watch, launched during the same year that gave us the first Apple II home computers, powered by a form of nuclear energy generation that has been slowly, steadily, irreversibly weakening for nearly half a century. And yet it continues, faithfully, patiently, to do exactly what it was built to do. Observe, measure, and faithfully report back whatever it finds across a distance so vast that the very act of communication itself has become an exercise in genuine, extended patience. Let's go back now, properly, to the beginning of this long, remarkable journey. Because before Voyager 1 became the quiet, distant interstellar explorer we're going to spend most of tonight discussing, it was, for a brief, spectacular period in the late 1970s and early 1980s, one of the most productive planetary science missions in the entire history of space exploration. Voyager 1's first great encounter came at Jupiter in March of 1979, and what it found there transmitted back to Earth in a slow, patient stream of data that took scientists weeks and months to properly process and analyze, permanently, fundamentally changed our understanding of the entire outer solar system. Perhaps the single most famous discovery from this Jupiter flyby involved one of Jupiter's 4 large moons, a small, rocky world called Io prior to Voyager 1's arrival. Scientists had generally expected Io to resemble our own moon, a cold, ancient, cratered surface, geologically dead, unchanged for billions of years. Instead, as Voyager 1's cameras swept past Io, a young engineer named Linda Morabito Carefully examining one of the navigation images taken to help track the spacecraft's own precise trajectory, noticed something genuinely strange along the moon's edge. A faint, umbrella-shaped plume rising more than 150 miles above Io's surface. It was a volcanic eruption, an active one, captured, entirely by accident, in the background of an ordinary navigation photograph. Io, it turned out, was not a cold, dead world at all, but the most volcanically active body anywhere in our entire solar system. Its surface constantly, violently reshaped by the immense tidal forces exerted by Jupiter's overwhelming gravity, squeezing and stretching the small moon's interior with such tremendous force that it generates heat considerably beyond anything our own planet's interior produces. Voyager 1 also discovered, during this same historic Jupiter encounter, a thin, previously unknown ring system encircling the giant planet, along with two entirely new moons. Small, previously undetected worlds named Thebe and Metis, hiding, until that moment, in the overwhelming glare of Jupiter's own considerable brightness. From Jupiter, Voyager 1 continued outward, arriving at Saturn in November of 1980. The encounter that would prove to be its final planetary flyby, and the one that, through a carefully planned gravitational trajectory, would ultimately fling it out of the plane of our solar system entirely, setting it on the long, patient course toward interstellar space it continues to follow to this very day. At Saturn, Voyager 1 discovered 5 entirely new moons, along with a previously unknown ring feature that scientists named the G-ring. But perhaps its most scientifically significant contribution at Saturn involved a much smaller, considerably more focused target. Titan, Saturn's largest moon, and, at the time, one of the more genuinely mysterious objects in our entire solar system. Titan, uniquely among all the moons in our solar system, possesses a thick, substantial atmosphere. Dense enough, in fact, that Voyager 1's cameras, however carefully aimed, could not actually see through it to the moon's surface below. This was, in its own way, a genuinely important discovery. Confirmation that this small, distant moon, orbiting so far from the Sun that its surface temperature hovers around -290 degrees Fahrenheit, nonetheless possessed an atmosphere thick enough to completely obscure whatever lay beneath it. This specific mystery, what does Titan's surface actually look like, hidden beneath its thick, orange, nitrogen-rich haze, would remain genuinely unsolved for another quarter century, until the Cassini-Huygens mission, launched considerably later, finally managed to send a small probe directly down through that thick atmosphere in 2005, revealing, for the first time, a genuinely alien landscape of methane lakes and hydrocarbon rain, a world simultaneously familiar in its basic geological processes and utterly foreign in its specific chemistry. But that discovery, remarkable as it eventually proved to be, traces its origins directly back to Voyager 1's own patient, careful observations in 1980. The first confirmation that something genuinely strange and genuinely interesting was hiding beneath Titan's thick, obscuring clouds. Wherever you are, I hope you're comfortable. After this historic Saturn flyby, Voyager 1's planetary science mission was, in a very real sense, complete. Its trajectory, carefully calculated by mission planners years earlier, would carry it up and out of the flat orbital plane in which all the planets travel, meaning it would never again pass close enough to any other body in our solar system to conduct another meaningful scientific flyby. What it would do instead, across the following decades, was simply continue outward, faithfully, patiently, carrying its instruments, its golden record, its small, quiet cargo of human music and greetings and images, further and further from the only home it had ever known. And in February of 1990, more than 12 years after its original launch, at a distance of roughly 3.7 billion miles from Earth, a fraction of where it currently sits tonight, Voyager 1's cameras were turned around, one final time, at the specific request of the astronomer and science communicator Carl Sagan, to look back toward the inner solar system it had left so far behind. The resulting photograph, later famously described by Sagan himself, captured Earth as it appeared from this extraordinary distance, a single, pale blue point of light, less than a single pixel across, caught within a scattered ray of sunlight, suspended, as Sagan so memorably put it, on a mote of dust suspended in a sunbeam. Shortly after taking this final, historic photograph, Voyager 1's cameras were permanently switched off. A deliberate, careful decision by mission engineers, made specifically to conserve the spacecraft's steadily diminishing electrical power for the instruments considered most scientifically valuable for its next, considerably longer chapter, the long, patient journey toward, and eventually through, the very edge of our solar system itself. Let's talk now, properly, about what that next chapter actually involved. Because the story of Voyager 1's journey through, and eventually beyond, our solar system's outer boundary is, I think, considerably less widely known than its earlier planetary triumphs, and deserves, tonight, our full and patient attention. For more than 2 decades following its final planetary encounter at Saturn, Voyager 1 continued its long, quiet journey outward, gradually approaching and eventually crossing the boundary of what scientists call the heliosphere, the vast, invisible, protective bubble carved out by our own sun's continuous outward breath of charged particles, which we explored together in considerable detail in a recent conversation here at Late Space. On August 25th, 2012, 35 years after its original launch, Voyager 1 became the first human-made object in history to cross this boundary and enter genuine interstellar space. This was, by any reasonable measure, one of the truly historic moments in the entire history of space exploration. A machine, built by human hands using 1970s-era technology, traveling far enough, faithfully enough, patiently enough, to finally leave the protective embrace of our entire solar system behind and begin transmitting, for the very first time in our species' history, direct measurements of the genuine space between the stars. And it is in the years since this historic crossing, the years we're going to spend the remainder of tonight properly exploring, that Voyager 1 has continued to reveal genuinely surprising, genuinely important discoveries about this previously unmeasured region of space, even as its own instruments, one by one, have been carefully, deliberately powered down in a patient, ongoing effort by mission engineers to preserve whatever remains of its steadily weakening nuclear power supply. Here is, I think, one of the more remarkable, more quietly moving aspects of Voyager 1's continued operation. It runs, even now, in 2026, on the same basic type of power source it launched with nearly 50 years ago. 3 radioisotope thermoelectric generators, devices that convert the heat produced by the slow, steady, natural radioactive decay of plutonium-238 into usable electrical power. This power source has no moving parts, requires no maintenance, and simply, faithfully continues its work through the patient physics of radioactive decay. But it also, inevitably, gradually weakens over time, losing approximately 4 watts of available power with each passing year. This means that, across nearly 5 decades of continuous operation, Voyager 1's engineers have faced an ongoing, increasingly difficult challenge, deciding carefully, deliberately, which of the spacecraft's original 10 scientific instruments can continue to receive power, and which must, reluctantly, be permanently switched off in order to preserve enough remaining electrical capacity to keep the spacecraft's most essential systems, its heaters, its communications equipment, its most scientifically valuable remaining sensors, properly functioning. As of 2025, only a small handful of Voyager 1's original instruments remained active, and even these final few are now carefully, deliberately being considered for retirement, as mission engineers work to stretch the spacecraft's remaining power for as long as scientifically possible, hoping, quite genuinely, to keep at least the magnetometer and the plasma wave subsystem. the two instruments most directly useful for studying the genuine interstellar environment. Operational for as long as the dwindling power supply allows. Wherever you are, I hope you're comfortable. Let's talk now, properly, about what these remaining instruments have actually found in the years since Voyager 1 crossed into genuine interstellar space. Because this is, I think, where tonight's conversation becomes genuinely, quietly fascinating. The first thing worth understanding is something we touched on briefly in an earlier conversation together. Voyager 1's own plasma science instrument, the sensor specifically designed to directly measure the density and behavior of charged particles surrounding the spacecraft, had actually stopped functioning years before the spacecraft's historic 2012 heliopause crossing, a mechanical failure dating back to shortly after its 1980 Saturn flyby. This meant that, for a considerable period following its crossing into interstellar space, scientists could only infer, indirectly, through other available instruments, that Voyager 1 had genuinely entered this new environment, rather than measuring it as directly and cleanly as they might have preferred. But in 2017, and again more thoroughly in subsequent years, Voyager 1's mission team discovered something genuinely remarkable, entirely unplanned by the spacecraft's original 1970s-era designers. They could use one of Voyager 1's other remaining instruments, the plasma wave subsystem, originally designed for a considerably different purpose: to indirectly measure the density of the surrounding interstellar plasma by carefully listening for the natural oscillations this plasma produces whenever it's disturbed by outbursts of solar activity arriving from our own distant sun. This discovery, genuinely clever, genuinely resourceful, allowed scientists to properly compensate for the earlier loss of Voyager 1's dedicated plasma instrument using a different tool, in a way its original designers had never specifically anticipated, to continue gathering genuinely valuable scientific data about the specific character of the interstellar medium surrounding the spacecraft. And what this data revealed, patiently, across the years since Voyager 1's historic 2012 crossing, has genuinely surprised the scientists studying it. Let me walk through some of these specific findings, carefully, because each one reveals something genuinely worth properly understanding. The plasma density measurements gathered by Voyager 1 in the years since its heliopause crossing revealed something scientists had not fully anticipated. The density of interstellar plasma appears to increase, gradually, steadily, the further Voyager 1 travels from our solar system's boundary. This finding suggested that our own solar system's protective heliosphere, rather than existing within a perfectly uniform, unchanging bath of surrounding interstellar material, instead occupies a genuinely varied, genuinely textured cosmic neighborhood, one where the specific density and character of the surrounding interstellar medium changes meaningfully, depending on the exact direction and distance you happen to be measuring from. Voyager 1's magnetometer, the instrument specifically designed to measure the strength and direction of surrounding magnetic fields, revealed something else genuinely unexpected: that the interstellar magnetic field immediately beyond our own solar system's boundary appears to be oriented in almost exactly the same direction as our own sun's magnetic field. This was, and remains, a genuinely surprising finding, because earlier theoretical models had generally predicted that crossing into genuine interstellar space should involve passing through a region where the magnetic field's direction shifted noticeably, marking a clear, measurable transition between our own solar system's specific magnetic environment and a genuinely separate, differently oriented Interstellar 1. Merav Ofer, a heliophysicist who has worked extensively with this Voyager data, and whom we discussed in our earlier conversation about the space beyond our solar system, described this specific, ongoing puzzle with genuine scientific candor. The interstellar medium immediately beyond our solar system's boundary, as directly measured by both Voyager spacecraft, does not appear calm or uniform or cleanly separate from our own sun's continued influence. It appears, instead, considerably more agitated, considerably more genuinely connected to and influenced by our own sun's ongoing activity than earlier, simpler theoretical models had properly anticipated. There is a third finding from these same years of patient interstellar observation that I find particularly worth sitting with tonight, here in this specific quiet. In 2021, a researcher named Stella Ocker, then a graduate student at Cornell University, was carefully analyzing years of accumulated data from Voyager 1's plasma wave instrument when she noticed something genuinely unprecedented: a faint, continuous, persistent electromagnetic hum present in the data almost constantly, rather than only during the brief, dramatic episodes triggered by outbursts of solar activity that scientists had previously focused most of their attention on. This wasn't the kind of dramatic, easily explained signal produced when a coronal mass ejection from our distant sun happens to reach Voyager 1's location, causing the surrounding plasma to briefly ring in a manner scientists could use to measure its density at that specific moment. This was something quieter, steadier, more continuous. A persistent, gentle background electromagnetic murmur present in the surrounding interstellar plasma, seemingly independent of any specific solar event, existing simply as a genuine, ongoing feature of the interstellar environment itself. NASA later released a short audio conversion of this signal. The actual electromagnetic oscillations detected by Voyager 1 translated into a frequency range audible to human ears. The resulting sound is faint, eerie, and genuinely strange, a thin, wavering tone, rising and falling gently, unlike anything in ordinary human experience, and yet, in its own quiet way, genuinely, hauntingly beautiful. This is, I think, worth sitting with properly. An actual sound, produced by an actual, physical process, occurring right now in genuine interstellar space, more than 15 billion miles from where you're currently resting, captured by an instrument built nearly 50 years ago, using 1970s-era engineering, and only properly understood, only properly recognized as scientifically significant in the more recent years of Voyager 1's remarkably extended mission. Wherever you are, I hope you're still comfortable. Let's talk now, for a while, about something more recent still. A discovery, or rather a series of ongoing observations that continues, even now, in this current year, to shape how NASA's engineers and scientists think about Voyager 1's remaining, carefully managed lifespan. In February of 2026, during one of Voyager 1's regularly scheduled roll maneuvers, a routine procedure conducted periodically in which the spacecraft rotates slightly in order to recalibrate its magnetometer instrument. Mission engineers noticed something concerning: an unexpected drop in the spacecraft's available power levels. This was not, immediately, a catastrophic problem, but it was genuinely, seriously concerning, because any further, unplanned decline in available power could potentially trigger Voyager 1's own automated safety systems. Specifically, a protective mechanism called undervoltage fault protection, which is designed to automatically shut down non-essential systems whenever the spacecraft's power levels drop below a certain critical threshold, in order to prevent a more serious, potentially unrecoverable failure. Faced with this genuine, immediate concern, the mission team made a careful, deliberate decision to permanently power down Voyager 1's low-energy charged particle instrument, an instrument that had been running almost continuously since the spacecraft's original 1977 launch, through nearly 49 consecutive years of faithful, uninterrupted operation. Stamatios Krimigis, the instrument's principal investigator, who has worked with this specific piece of scientific equipment since Voyager 1's original design and construction, wrote about this particular shutdown with genuine, evident warmth. Noting that the instrument's small internal scanning motor had continued rotating, faithfully, patiently, even after its supplemental heater was switched off, to conserve additional power, continuing its steady, mechanical work even as the surrounding temperature dropped to a genuinely extreme 62 degrees below 0°C. That it continued operating properly, faithfully, under these considerably challenging conditions was, in Crimigis's own words, quite simply, the stuff that dreams are made of. This particular instrument shutdown, on Voyager 1, mirrored a similar, slightly earlier decision made regarding its twin spacecraft, Voyager 2, whose own equivalent instrument had been switched off roughly a year earlier, in March of 2025. The two spacecraft, launched within weeks of each other back in 1977, continue, even now, nearly 5 decades later, to follow remarkably similar, carefully coordinated paths through their own gradual, patient technological decline. Their engineering teams working closely together, sharing decisions and strategies, treating both aging spacecraft as a single, coordinated, long-term mission, even as they travel now in genuinely different directions through interstellar space. What continues to motivate this careful, patient, ongoing engineering effort? The specific decisions about which instruments to preserve, which to reluctantly retire, how precisely to manage each spacecraft's steadily diminishing power supply, is a simple, genuinely important fact. There is currently no other spacecraft, anywhere, capable of directly, physically measuring the specific interstellar environment that Voyager 1 and Voyager 2 currently occupy. The New Horizons spacecraft, which we've discussed together in previous conversations, is expected to eventually cross its own heliopause boundary sometime around 2030, but its own onboard power supply is not expected to remain functional for many years beyond that milestone. A dedicated, purpose-built interstellar probe mission, specifically designed from the outset to study this region in considerably greater scientific detail, remains, for now, only in the earliest stages of formal proposal and consideration. For the foreseeable future, then, Voyager 1 and Voyager 2 remain our only direct, physical sources of information about this genuinely unique cosmic environment. A responsibility their engineering teams continue to take, quite visibly, quite genuinely seriously, carefully rationing every remaining watt of available power, in the patient hope of preserving at least some scientific capability for as many additional years as the physics of radioactive decay will allow. Wherever you are, I hope you're comfortable. I want to spend some time now, properly, sitting with a specific, quiet piece of the story I mentioned earlier, because I think it deserves considerably more than a passing reference. Voyager 1 carries, bolted securely to its side, a 12-inch, gold-plated copper phonograph record. The same golden record we've discussed together in earlier conversations here at Late Space. Inside its careful, deliberately chosen grooves, greetings recorded in 55 different human languages, the music of Bach and Chuck Berry, and traditional folk musicians from cultures scattered across our entire planet, the natural sounds of Earth itself, wind, rain, thunder, the calls of whales and birds, a mother's heartbeat, the electrical patterns of a human brain, recorded specifically while its owner sat quietly, deliberately thinking about the particular experience of being in love. This record, carefully assembled by a committee chaired by Carl Sagan himself back in 1977, was designed, quite deliberately, quite intentionally, to survive for an extraordinarily long time. The gold plating specifically chosen for its remarkable resistance to corrosion, even across timescales measured in many hundreds of millions, quite possibly billions, of years, travelling through the genuine, near-perfect vacuum of interstellar space. Right now, tonight, this record continues its own long, silent journey, 15,800,000,000 miles from the specific studio where it was originally recorded and assembled nearly 50 years ago. It will not encounter another star system for approximately 40,000 years. A specific, calculated close approach to a star called Gliese 445, which we discussed together, at some length, in an earlier conversation here at Late Space exploring Voyager's genuinely distant future. There is something, I think, genuinely worth sitting with in this specific detail, that the same small, patient, aging spacecraft currently teaching us new things about the physics of the interstellar magnetic field and the peculiar behavior of galactic cosmic rays, is also, simultaneously carrying forward this small, careful, deliberately chosen message. A message that will likely outlast our entire civilization, outlast our species itself, quite possibly outlast every trace of human presence anywhere else in the universe, patiently, silently continuing its journey long after everyone currently listening to these words has died, long after the specific language I'm speaking to you in right now has changed beyond recognition or vanished from use entirely. Let's talk now, for a while, about the specific people behind this remarkable, ongoing mission, because I think their patient, dedicated work deserves genuine, proper attention here at this hour, in this particular quiet. Suzanne Dodd has served as the Voyager mission's project manager since 2010, meaning she has personally overseen this specific spacecraft's operations for considerably longer than many entire careers typically last. She joined the broader Voyager team originally back in 1984, while Voyager 2 was still traveling between Saturn and Uranus, meaning her own personal, professional relationship with this mission now spans more than 4 decades. In discussing the mission's continued operation, Dodd has spoken openly about her own specific, personal hope to see at least one of the 2 Voyager spacecraft reach its 50th anniversary of continuous operation in 2027, a date now less than a year away. Given everything the mission team has already successfully overcome across these past several decades, a set of stuck thrusters, successfully revived through careful, patient engineering work in 2017, a corrupted onboard memory system, successfully repaired in 2024, a temporary communications anomaly successfully worked around in late 2024 when the spacecraft briefly, unexpectedly switched over to its own onboard backup transmitter. Dodd and her colleagues believe this particular 50th anniversary milestone remains genuinely, achievably within reach. I find something genuinely moving, properly sat with in this specific detail. A woman who has devoted the majority of her own professional career, more than 4 decades of careful, patient, dedicated work to the continued operation of a single spacecraft, built before she herself had even joined its mission team, expressing a simple, genuine, deeply personal hope that this particular machine, this particular faithful, aging emissary, might continue its work for just a little while longer. Wherever you are, I hope you're still comfortable. Let's talk now, for a while, about something the mission team has recently attempted. A genuinely bold, genuinely high-stakes engineering intervention, specifically designed to help preserve Voyager's remaining operational capability for as long as possible. Engineers at the Jet Propulsion Laboratory have recently begun implementing what they've informally nicknamed, with a particular kind of dry, engineering humour, the Big Bang. A coordinated, high-stakes power management manoeuvre designed to buy both spacecraft additional operational time by simultaneously reorganizing which specific components draw power from the steadily diminishing supply. The specific idea involves turning off certain systems previously used to maintain particular components at their normal operating temperature, replacing them with alternative, lower power heating solutions in the hope of freeing up additional electrical capacity for the spacecraft's most scientifically valuable remaining instruments. This is genuinely a delicate, high-stakes procedure. Removing carefully maintained heat from systems that have operated continuously at stable temperatures for nearly 5 decades carries real, meaningful risk, and there is no guarantee that either spacecraft will successfully survive the transition without some kind of unexpected complication. The team has chosen to implement this specific maneuver first on Voyager 2, reasoning that its slightly greater remaining power reserves and its somewhat closer proximity to Earth make it the marginally safer candidate for this particular experimental procedure. If Voyager 2 successfully survives this transition, continuing to operate normally afterward, the same procedure will subsequently be attempted on Voyager 1 as well, though not before July of 2026, according to the team's current, careful planning. There is, notably, a specific hope embedded within this careful engineering strategy. If the maneuver proves successful, there remains a genuine possibility that that Voyager 1's own low-energy charged particle instrument, the one we discussed earlier, reluctantly powered down in February of 2026, could potentially be switched back on. The instrument's small scanning motor, notably, has been deliberately left running at a bare minimum power level of just half a watt, specifically to prevent it from mechanically seizing, preserving, quite deliberately, this specific possibility for the future. I want to sit with this particular detail properly, because I think it reveals something genuinely worth carrying with you tonight, here, at this hour, in this particular quiet. A team of engineers, working with a spacecraft built before most of them were even born, continuing the careful, patient, technically demanding work of their own predecessors and mentors, many of whom have since retired or passed away, but whose original design decisions, whose careful documentation, whose accumulated institutional knowledge continues, faithfully, to inform every subsequent decision made about this remarkable spacecraft's continued operation, choosing, quite deliberately, to preserve even the smallest, most modest possibility of future scientific return, simply by keeping a tiny motor running at half a watt, patiently, faithfully, in the genuine hope that it might, someday soon, be properly, fully reactivated. This is, I think, exactly the kind of patient, careful, genuinely hopeful work that defines the very best of scientific and engineering practice. Not dramatic, not headline-grabbing in any particular moment, but steady, dedicated, quietly persistent, carried forward across genuinely long stretches of time by people who understand, quite clearly, that their own specific contribution is simply one careful link in a much longer, much larger chain of effort, stretching back to 1977, and, they genuinely hope, continuing forward for at least a little while yet. Let's widen our view now, gently, and talk about what all of these specific, patient discoveries actually mean, taken together, for our own broader understanding of the universe surrounding us. Before Voyager 1 and Voyager 2 crossed into genuine interstellar space, our entire scientific understanding of this environment rested on theoretical models and indirect inference. Careful, well-reasoned predictions, built from what we could observe and measure from within our own solar system's protective boundary, but never actually physically confirmed through direct measurement. The patient data these two aging spacecraft have gathered, across more than a decade of continuous interstellar travel now, has fundamentally, permanently improved our understanding of this previously unmeasured region. We now know, with genuine confidence, that the interstellar magnetic field immediately surrounding our solar system's boundary is oriented in a genuinely surprising, still not fully understood way. We know that cosmic rays arrive from this environment with a genuine, measurable directional preference, rather than uniformly from every direction, as earlier models had predicted. We know that our own sun's activity continues to meaningfully influence conditions considerably further into interstellar space than previous theoretical models had properly anticipated, and we possess, now, an actual recorded sound. A faint, genuine electromagnetic hum translated carefully into human hearing range, representing the actual physical character of the specific interstellar environment surrounding these two small, faithful spacecraft right now, tonight. None of this represents the kind of dramatic, headline-grabbing discovery that dominates popular science coverage. There is no single, sudden, revolutionary breakthrough here, no moment of instant, complete understanding. What Voyager 1 and Voyager 2 have provided, instead, across their remarkably extended interstellar mission, is something considerably quieter, considerably more patient, and, I think, considerably more genuinely valuable. A slow, steady, carefully accumulated body of direct, physical evidence, gradually, patiently improving our understanding of a genuinely unique cosmic environment that no other instrument, before or since, has ever actually, physically visited. Wherever you are, I hope you're comfortable. Let's talk now about what comes next. Because Voyager 1's story, remarkable as it already is, remains genuinely, actively ongoing right now in this current moment. In the coming months, as Voyager 1 continues its steady approach toward that historic one light day milestone in November of this year, mission engineers will continue their careful, ongoing work, monitoring the spacecraft's steadily diminishing power supply, making difficult, deliberate decisions about which remaining instruments to preserve and which to reluctantly retire, and continuing to attempt the kind of careful, high-stakes engineering interventions, like the power management maneuver we discussed a few minutes ago, specifically designed to extend the spacecraft's remaining operational lifespan for as long as the underlying physics will genuinely allow. Beyond November's specific light day milestone, the mission team's primary remaining goal involves simply, patiently, reaching Voyager 1's 50th anniversary of continuous operation in September of 2027, a date now genuinely, meaningfully within reach, though not, by any means, guaranteed. And beyond even that considerable milestone, the honest, sober reality is that Voyager 1's remaining operational lifespan is now genuinely, measurably limited. Its nuclear power source continues its slow, steady, irreversible decline, and at some point, perhaps within the next several years, perhaps with careful, dedicated engineering effort, somewhat longer than that, the spacecraft will finally, quietly fall silent, its last remaining instruments unable to draw sufficient power to continue functioning, its final transmission traveling, patiently, faithfully, across an ever-growing distance, until it finally, eventually reaches whatever antenna happens to be listening for it here on Earth. I want to spend some time now, gently, sitting with what this eventual, inevitable silence will actually mean, because I think it deserves proper, honest, careful attention here at this hour, in this particular quiet, rather than being simply glossed over or avoided. When Voyager 1 finally, eventually stops transmitting, whether that happens next year or in 5 years, or, with sufficiently careful, dedicated engineering effort, considerably longer than that, it will not simply disappear. It will continue, faithfully, silently, exactly as it has for nearly 5 decades already, moving steadily outward at 17 kilometers per second, carrying its small, careful cargo of human music and human voices and human memory, drifting patiently through the genuine dark between the stars, entirely unaware, in any meaningful sense, of whether anyone back on Earth continues to listen for its voice. This is, I think, one of the more quietly profound aspects of Voyager 1's entire remarkable story. The specific, deliberate distinction between a spacecraft's active scientific mission, which will, inevitably, someday soon, come to its own natural, careful conclusion, and the spacecraft's continued, ongoing physical existence, which will persist, faithfully, for a considerably longer span of time, for the thousands of years required to reach its first genuine stellar encounter, and, quite possibly, for a considerably longer span still, stretching outward toward timescales we discussed together, in careful, patient detail, in an earlier conversation exploring Voyager's genuinely distant future. The specific voice we've been listening to tonight, the faint, patient hum of genuine interstellar plasma, the careful, deliberate measurements of magnetic field strength and cosmic ray behavior, the ongoing, 90-hour, back-and-forth conversation between a small, aging spacecraft and the patient engineers still listening for its signal. This particular voice will someday eventually fall silent. But the spacecraft itself, the small, careful, physical object currently drifting 15,800,000,000 miles from where you're resting tonight, will continue, faithfully, for considerably longer than any of us currently listening to these words will ourselves remain alive to witness. Let's bring this conversation back, now, gently, towards something a little more immediate, a little more personal, before we begin the slow, careful work of properly closing tonight's conversation. You are, right now, tonight, living through a genuinely unique, genuinely historic period in this remarkable mission's now nearly 50-year story. Within the next several months, Voyager 1 will cross a threshold. One full light day from Earth that no human-made object has ever crossed before, and, quite possibly, none will cross again for a considerable span of time still to come. This is not, properly understood, a distant, abstract, purely theoretical milestone. It is happening, right now, this year, in genuine, measurable, ongoing real time. A small, faithful spacecraft, built by human hands nearly 5 decades ago, continuing its steady, patient journey outward, while a team of dedicated engineers, some of whom have devoted the majority of their own professional careers to this single, remarkable mission, continue their own careful, patient work, managing dwindling power supplies, making difficult decisions about which instruments to preserve, and continuing to listen, faithfully, for whatever this small, distant machine might still have left to teach us. There is something, I think, genuinely worth carrying with you into sleep tonight, in properly understanding that this particular story continues, right now, in genuine, ongoing real time. That somewhere, tonight, in a control room in Southern California, engineers are monitoring incoming data, patiently calculating power budgets, carefully planning the next careful step in this small spacecraft's continued, extended operation. You are not simply hearing about a historical event, safely completed and properly filed away. You are hearing about something genuinely, actively unfolding right now in this current moment. A quiet, patient, ongoing act of human curiosity and dedication, continuing steadily outward, 15,800 million miles from wherever you happen to be resting tonight. Let's come down now, slowly, gently, toward the end of tonight's long conversation. Here is what is true, as carefully and as honestly as I can leave it with you. Voyager 1, launched in September 1977, currently sits approximately 15,800 million miles from Earth, a distance so vast that a radio signal traveling at light speed requires nearly 23.5 hours simply to make the one-way journey. In November of this year, it will become the first human-made object in history to reach one full light day from Earth, a distance of nearly 16 billion miles, requiring a full 24 hours for any signal to travel between the spacecraft and home. Across its remarkable, nearly 50-year mission, Voyager 1 discovered active volcanic eruptions on Jupiter's moon Io, previously unknown rings and moons around both Jupiter and Saturn, and confirmed Titan's thick, mysterious atmosphere. Discoveries that permanently, fundamentally reshaped our understanding of the outer solar system. And in the years since crossing into genuine interstellar space in 2012, it has continued to reveal genuinely surprising findings. An interstellar magnetic field oriented in unexpected alignment with our own sun's field. A directional pattern in incoming cosmic radiation that earlier models had not predicted. And a faint, persistent, genuinely beautiful electromagnetic hum, representing the actual physical character of the space between the stars. Its power supply continues to weaken, gradually, irreversibly, forcing careful, difficult decisions about which remaining instruments to preserve. But a dedicated team of engineers, some of whom have devoted decades of their own careers to this single mission, continue their patient, careful work, hoping, genuinely, to see this remarkable spacecraft reach its 50th anniversary of continuous operation in 2027. I want to leave you with one final image before we close, because I think it captures, better than any additional detail could, the particular feeling I hope you carry with you into sleep tonight. Picture, if you can, a small, aging spacecraft. Roughly the size of a compact car, built using computer technology considerably less sophisticated than a modern pocket calculator. Drifting, right now, this very moment, through the genuine, physical dark between the stars, 15,800 800 million miles from wherever you happen to be resting tonight. Its cameras have been silent since 1990. Most of its original scientific instruments have been carefully, deliberately powered down, one by one, across nearly 5 decades of patient, careful engineering decisions. But a small handful of sensors continue their faithful work, patiently measuring the strength of surrounding magnetic fields, listening carefully for the faint, genuine hum of interstellar plasma, faithfully transmitting whatever they discover back across an ever-growing distance toward a small, dedicated team of engineers who continue, faithfully, patiently, to listen. And bolted securely to its side, a small, golden record continues its own silent journey, carrying forward into a future none of us will live to see, the music and the voices and the simple, deliberate hope of the people who built and launched it nearly 50 years ago. Thank you for spending tonight here. Thank you for letting something this small, this distant, this quietly remarkable become something worth understanding properly, carefully at this hour. Sleep well. And somewhere, right now, 15,800,000,000 miles away, continuing its long, patient journey outward, faithfully carrying forward everything we've ever tried to say about ourselves into the genuine dark beyond. Voyager 1 continues. Good night.